bipolar junction transistor. Okay, we have studied this in another subject called as analog electronic circuits, but that was just information required to study the application point of view. So bipolar junction transistor are also called as BJT. Okay, so it's a three-terminal semiconductor device. So BJT is a three-terminal semiconductor device. It has two junctions. Now, what are the three terminals? Can anyone tell me?
Base emitter collector.
Yes. So we have emitter, base, collector. These are the three junctions. They are made up of, let me write it outside. So this is emitter, base, and collector. They can be made up of NPN or PNP. Yes or no? So these are the three terminals. What are the two junctions? So we have base emitter junction over here. So this is base emitter junction, and the other one is base collector junction, right? Which is the larger junction? Base collector, right? This is base collector junction. So basically, we know also that the BJT operates in four operating modes. Okay. So what are the four operating modes? First is the forward active mode. Then second one, saturation.
Saturation.
Then cutoff, then cutoff, and reverse active. Reverse active we are not seeing. Now let us check the status of the junctions over here, base collector and base emitter. So in the active mode, base emitter junction will be forward bias and base collector will be reverse bias. In saturation, both will be forward bias, and in cutoff, both will be reverse bias. So please remember this table, the status of the BJT uh, under three operating modes. Yes or no? Now, what is so special about the base, emitter, and collector? So out of this, emitter is the heavily doped. So emitter is made up of actually N plus. It's heavily doped. So we can write emitter is heavily doped. That is high concentration of ND. If it is an NPN transistor, it is heavily doped so that it can inject large number of charge carriers into the base. Now base is lightly doped and it is very thin. We have understood why it is very thin before, but we'll try to understand. So a base is lightly doped and very thin because it passes most of the injected charge carriers from the emitter to the collector. So that a lesser recombination happens in the base terminal. And what about the collector? Collector has the largest area. So it has a larger area and moderately doped, because it has to collect all the injected electrons from the emitter towards the base and it is collected at the collector terminal. So this is it. Okay. So the two symbols of the BJT are as follows. This is N, P, N, and how we draw PNP? The arrow is inward. What does the arrow indicate? Anyone? Arrow indicates the direction of the emitter current. Is it not? Hello, yes or no?
Yes, sir.
Yeah. So we have already seen its, working in brief. Today we'll go about the structure, how the structure is, and what are the basic things. So other things which to know about BJT are as follows. So you should know what is the alpha. What is alpha? Common base current gain. Yes or no? And what it is given by? IC by IE. There is one beta also. Beta is IC by IB. It is common emitter current gain. Yes or no? And how the three currents are related in the circuit in a BJT? I emitter current is collector current plus base current. So these three are the primary three things which you should know about a BJT. Also, we should also know about the leakage currents. So we say IC is beta IB. There's a leakage current plus I C E O. This is the amount of leakage current. Okay. And what's the relation of ICEO and ICBO? So ICEO is 1 plus beta times ICBO. So is the current flowing through the collector and emitter with base open. ICBO is the current flowing through the collector and base when the emitter is open. So these are the relations, few relationships which we should know. Okay. Yes or no, students? Agree?
Yes,
Then
sir.
we go for, it's
Yes.
just a revision going on basically. So we have common emitter characteristics now upcoming. We will discuss this quickly and we'll go to the physics of it, why it is related. So for common emitter characteristics, we have the BJT over here. Then we have a resistor over here, a power supply over here. Similarly, a resistor and a supply over here. And it's in the common emitter mode configuration. This is grounded. This will be VBB. This is RB. This is IC. And this is VCC. How are the three currents flowing? Base current is going inside, and between this we have VBE. Between these two terminals, it is VCE. The current which is flowing over here into the collector terminal is IC. Okay, and current leaving over here is IE. Right. So how will be my input characteristics of the device? Input characteristics of the device, which we have seen earlier, it's VBE upon, I mean, IB versus VBE at different values of constants called as VCE. So this is how the characteristics will be. Okay, what are these values? VCE 1 or 2, which is greater. Then this is let's say 10. This is let's say 5 first one. This is for 10. So this is the way it is increasing VCE. Okay, this was the input characteristics. So from the input characteristics, what information do you get? In of the device. Yes or no? Delta VB upon delta IB. Agree? Yes or no? So
Yes,
this is
sir.
my input characteristics, just like a revision I already told you all. Now we'll go for the output characteristics. The output characteristics will tell the great deal about the transistor operation. So this is my VCE versus collector current IC in milliamperes. Now the characteristics will look something like this. We have a small graph just parallel to the x-axis here. This indicate leakage current. Okay, so this is actually my cutoff region. Then we have a graph like this. Okay, so what are the three operating regions over here? This is my saturation region, which I marked over here. This is saturation, and the remaining this region is the active region. And we want to operate the device in the active region, and this is my cutoff. All right, these are different values of IB. So this is IB equal to 0. This is IB equal to 5 micro. This is IB equal to 10 microamperes. Yes or no? So this output characteristics will tell the operating regions of the MOSFET where I am. Then we can also calculate R out from the output characteristics, or it is also called as RO. How we can calculate R out of this BJT? It is delta VCE upon delta IC. So that is how we can calculate R out. We can also calculate beta, delta IC upon delta IB. So we can extract this parameters from the characteristics, output characteristics. So this is output characteristics of BJT, of NPN BJT. Okay, beta is the current gain, output is the R out is the output resistance of the BJT. All right. Can anyone tell me what is early effect? Early effect. or it is also called as base width modulation. I've explained that in the other subject, but still, I want to ask you all, do you all remember what is early effect? What is the effect of early effect? The effect of early effect is that there is a slope in these characteristics which is not zero, this way. Yes or no? And if you extrapolate them back, you will get a common point which is called as the early voltage. Recollected? Yes or no? Okay. So for very large values of VC, due to early effect, very small changes in alpha will be reflected in a large change in beta. Okay, so that is the effect. All right, students. Hello.
Yes, sir.
Okay. Acha, why it is this BJT is called as bipolar? Anyone can know? Because the charge carriers, the current flow is due to both the type of charge carriers. And what are the charge carriers over here? Electrons and holes. Yes or no? Hello. Do you agree?
Yes, sir.
Okay. Now we come to the energy band diagram. We'll come to the energy short form is EBD of NP and BJT.
Sir, could you scroll to the previous slide for a second?
This one. This is all the
Ah, yeah.
revision which we have already
No,
done
no,
before.
yeah, I wrote everything. Thank you.
Yes, yes. Yeah. So now let us concentrate on the energy band diagram. And how does it operate? Very carefully. Okay. So let us say we have a NPN transistor like this. Okay. The emitter region over here, the base is 10. So this is my N, P, N. Okay. Please mark it. These are my emitter terminal. This is my base terminal. This is the collector terminal. Let me highlight the depletion region over here. So these are the depletion regions. The base emitter depletion region. So this is base emitter junction and this is base collector junction. All right. Now with respect to this, we have to draw the energy band diagram. So for the energy band diagram, what you need to do is extend it down all these things like this. Okay. Also extend this levels. The depletion region width will also come into picture here. From year to year, we can mention the depletion region. So use dotted lines only because we will be drawing overwriting it. We'll be overwriting them. That's why I draw with pencil first. Don't draw with pen in these things. Now, are you all ready? Or
Yes,
you
sir.
are still drawing?
Yes, sir.
Okay. So now we have drawing the NPN depletion. Energy band diagram of NPN BJT under zero bias. That means no external voltage is applied or it is under thermal equilibrium. So what happens in thermal equilibrium? Come on. The Fermi level will align itself, no?
Yeah.
So then thermal equilibrium, the Fermi level will be same for all the three semiconductors. By the way, all of them are made up of silicon. Silicon, silicon, silicon. If their material is different, then it is not silicon, it is a Different materials, heterojunction BJT it will be.
HBT.
Okay, if the materials are different. HBT, correct. Now, tell me, let's say the doping over here is slightly higher compared to doping over here. So now tell me how the energy band diagram will look like. Come on. This is my Fermi level throughout. So this is the formal Fermi level over here. So where will the conduction band come in this N plus region? Near to the Fermi level, right? So it will come over here. Yes or no? This will be EC. And by the energy band gap, this will be EF, valence band. So this will be the conduction band and this will be the valence band. Similarly on the, it's only up to the neutral region. This is the space charge region or the depletion region, right? Only up till here we can draw. And over here, since it is heavily doped, it will be closer to the Fermi level. Now this will be not be closer to the Fermi level. It will be over slightly above. Why? Because it is not so heavily doped. So this is conduction band. And where will be the valence band? Valence band will come in the similar manner down, EV. Okay. And what is the difference in the energy band gap? EG. Now, where will energy band diagram of p-type silicon will come? So the p-type silicon over here, EV will come near and EC will come above. Agree? Yes or no? So far you have understood how to draw? Can I complete it? Yes. So these will be
Yes,
drawing
sir.
in freehand. Now that is a discontinuity, right? So how they will be joining? Will they be joining a straight line? No, it will be gradually joining them. So you can gradually join them like this. Okay. And this also can be gradually down joined. This can be up and this can be down again. So this is my energy band diagram of NPN transistor of same material homojunction in zero bias conditions. So please draw energy band diagram of NP and BJT under zero bias. Okay, so please complete it. So as you know about this level, all states will be about a conduction band. All states are filled, and this is the valence band. So below this level, all states are occupied. Okay, and this is your energy band gap. This is your energy band gap. It will be same throughout. Remember that. So energy band gap will remain same. Did you understood how to draw the energy band diagram under zero bias?
Sir,
Yes.
but on the N side,
Uh-huh.
the EV the same at the same point as the EV on emitter side?
Yeah, understood. Understood. This will be slightly up and this will be slightly up. This also. Why? Because it is lightly doped, na? So lightly doped
Yeah.
means it is heavily doped. So that conduction band will be lower to the closer to the valence to the Fermi levels. Whereas over here it will be
Okay.
slightly away from the conduction band, indicating that it's
Okay.
a less N type material. But I've mistake I've done is this I've drawn on the same level. This should be slightly above. So that the EG
Okay.
remains same throughout. Understanding? So here also EG
Yes.
is same. Completed. So what happens it at zero bias, the net current density is zero. So over here, the current flowing through this through the BJT is zero under zero bias under thermal equilibrium. Why it is zero throughout the transistor? Because the net electron current density due to drift and diffusion is equal to zero. Similarly, the whole current density is also zero. Completed this, students? Yes or no? Can I scroll down?
Yes, sir.
Okay. Now, to understand the basic control action of the transformer, what we call it control action of BJT. To understand how does the BJT actually operate, we need to put a BJT in its one of the modes. So we will consider active mode, forward active mode. So what happens in the forward active mode? Let's say if this is my BJT, I have my emitter over here, I have my base over here. This is N, P, N. All right. This is emitter, base, collector. Okay. Now what are we doing is, how do we do it? Active mode of BJT. We consider base emitter junction to be what? Forward bias, right? So how do we connect it forward bias? This is N, so their negative will go. This is positive. So this is VBE, forward bias. What about the base collector junction? Base collector junction is reverse bias, meaning here you will connect negative and here you connect positive. So this is VCB. So according to this voltages, will there be a depletion layer over here also? Yes, slightly over here, and here it will be slightly bigger. Okay, so this is my base emitter junction. This is my base collector junction. And now I will draw the energy band diagram in relation to these dimensions. So this is the metallurgical junction between base and emitter. This is the metallurgical junction between base and collector. And these are my base emitter junction, depletion region. And here we have base collector junction, depletion region. So everything I am putting it over here. You remember how this energy band diagram was over here? Yes or no? It was like this, right? This is zero bias. This was emitter, base, collector, and this was EF. Now, what happens in the active mode? Can you tell me? Hello.
Amplification.
Sorry. What did you tell?
Amplification.
This. Uh, no, I didn't get you. VBE we apply and VCB we apply. So what will happen to the BJT energy band diagram? Acha, VB is forward bias or reverse bias? Is it forward bias? Come on, yes or no? Hello.
Sorry.
Is the base emitter junction forward bias or no? Yes or no? Forward bias or no? Base emitter junction is forward bias or no? Yes, it is forward bias over here, as you can
It
see
is.
connection. That's what I'm asking. But see here, emitter terminal is getting a negative potential. So the electrons which are present over here will try to go into the run away from this negative supply because like charges will repel, right? So these electrons will be pushed into the base region. So for by forward bias. So do you remember in forward bias what happens? Now base emitter is forward bias, right? So we'll concentrate on this. So what happens in forward bias? Your energy level will move up. Your Fermi level, Fermi energy level will try to move up. This energy level will try to move up. Why? Because you're applying forward bias to it, a negative voltage to it. Okay. So this level will move up. So this distance will get shorted. So this distance will be now less compared to this one. Okay. Now base collector junction is reverse bias. So what happens in reverse bias? We are applying a positive voltage to a negative supply, to an n-type semiconductor. So this energy level will go down. Are you listening what I'm doing? Why the
Yes.
particular energy level goes up and down? Because as of the applied voltages. So let us draw this diagram also. So there won't be a uniform Fermi level over here. Okay. How to draw this? Band gap will remain the same. So but first let me draw this. This is my Fermi level EFN, let's say. Okay. Where will my conduction band come? Here and here, right? Here and here. This is my conduction band. Agree? Yes or no? Hello.
Yes,
Yes,
sir.
sir.
Okay. Now, where will be the level over here in this EF? EF level will go up or down over here. This has gone up. This formula level has gone up. This will go down. Okay. Maybe across over here. Now here also we need to draw the EC and EV. So let's draw EC and EV with the same height. Okay. So this will be EC. This will be EFN on the other side. And this is valence band. Agree? Acha, what will happen to the energy level, Fermi level at base? So at the base, one point we are applying a negative potential, other point we are applying a positive potential. VB is around, let's say 0.7, but VCB can be higher, 5. So it is more negative than positive. Okay, so more negative means this level, understanding? This EF level will go try to go up. Did you all understand? So let me draw this level over here. It will try to go up. It no longer remains in the same position. So now if I draw the EC level and here it is. Okay, this is EC, EF and EV. Now how to draw it? So let me tightly draw down. Okay, this is EC, EF and EV. Now we have to join them together, right? Like this, smooth continuity, and this will be larger. Like this. Getting it? Yeah? This I should have drawn slightly above, like this. Okay. So what has happened over here? There are two depletion regions, this one. So this is base emitter junction. This is base collector junction. Okay. So what is this height given by now? This height will be this height. Earlier it was what? Into VBI. Now it will be Q into VBI minus VBE. So earlier this height was VBI, right? But now it will be Q into VBI minus VBE. Acha, what about this height? What about this height? How it will be given by Q into VBI plus VCB.
Yes.
Agree? Because now why this gap is small and this is big. Earlier the gaps were same, right? On the both the sides the barriers were same. So electrons have to, if an electron has to travel, these are electrons which are present over here, let's say. It has to apply tremendously high energy to reach the top and then topple over. But over here, in this case, in this energy band diagram, how will the electron can travel? Easily, right? From the emitter, they can topple this barrier, which is a small barrier, and go over here. Got it? Similarly, holes from the valence band on this side can go over here, this side. Are you understanding what I'm trying to do? So the electrons which are present, first of all, it has to overcome the energy band gap, then they will reach the conduction band. And if we apply a voltage across this emitter terminal and collector terminals, so this side of the energy band diagram reduces slightly and this side also increases. So due to that, what happens is any electron which is present over here, I'm drawing with circles, will topple over the barrier and will reach the collector side. This is actually what happens. Similar to the holes. Holes will topple from the collector side and go into the emitter side, because holes and electrons direction will be different. Okay. So these are electrons which are present available for conduction. They can move, if you apply the voltages, they start moving to the other side, to the collector. The more and more electrons starts getting collected at the collector terminal. Understood this? So this is my energy band diagram in forward active mode. So write down. Have you drawn this energy band diagram? Hello.
Yes, sir.
In forward, have you completed it? No, na?
Yes, sir.
Okay, completed it.
Sir,
Very
the
good. Did you all,
Fermi level is
which Fermi level? This one, na?
uh, in the
Ah,
diagram.
this is EFP. Which Fermi level?
No,
See,
no,
this is
yeah, I was
EFN
just
on the N side. This is EFN of the P of the N side again. What is happening is, instead of a negative
yeah,
voltage, you are applying positive voltage over here. So positive voltage will pull the Fermi level down. And why this Fermi level will go up? Because you are applying a negative voltage.
yeah,
Okay, and why this Fermi level will go up? Because you're applying a more negative voltage. So when we apply negative voltage, it increases the electronic energy. It rises to a particular level. Okay, so let's understand the basic control action of a transistor. Let us assume that here we are starting with the explanation. Let us assume that the base emitter junction is forward bias and the collector base junction is reverse bias. If so happens that this will be the most common state of operation. This for active mode or forward active mode is the most common state of operation in a BJT. All right. Hello. Yeah, understood about this topic?
yes.
Yes, sir.
Any queries you all have related to the drawing of the energy band diagram? Actually, properly, if you want to draw, you should have drawn like this. See, if you want to saw, this is my, I'm just drawing it in a short way. Don't get me wrong. Okay, this I have to draw it again properly. Here it is. This will be at zero bias. Yes or no? Having the same Fermi level. And over here, if you want, this is zero bias. Energy band diagram. And over here, how it will be? SF. Okay. So these are the two depletion regions. This is base emitter. This is base collector. Clearly, you see this is applied bias in active mode. And this is N, P, N. N, P, N. All right. So here we have applied positive VB and we are applied negative VBC. This is the active mode of operation. Okay, so the injection mechanism takes place over here from, so we can write injection is happening from emitter to base. From the emitter, electrons are getting emitted into the base terminal, and then they are getting collected at base and then transferred back to the emitter, to the collector. So these are the energy band diagrams which I think you have drawn already. Can we move ahead with this? Yes or no? Clear about this energy band diagram if they ask you? Acha, now for home assignment, you can draw, for home assignment, draw energy band diagram of PNP BJT, PNP BJT in zero bias and in forward active mode. I'm not doing it right now. You can try this on your own. Forward active mode. Okay. So draw the energy band diagram. We have drawn it for NPN. You draw it for PNP. Okay. Now, structurally, MOSFETs. We'll compare now MOSFETs with BJTs. MOSFET we have already studied. You all have studied, right? So MOSFET, in case of a depletion type device, it might use a reverse bias PN junction. So reverse bias PN junction is utilized over there in case of a MOSFET. If you see the substrate material in a MOSFET, right? So here it is a MOSFET. So this is N plus, this is N plus, this is the substrate. So basically, this is what we are saying, that a reverse bias PN junction exists over here like this, here and here. So this is the PN junction which we are talking about. Okay. This is P, this is N. So basically, this PN junction is oriented like this, because what happens, the substrate and the gate terminal, this is the drain terminal, this will be the source terminal. Oh, we draw over here source, and this is drain, and this is substrate. So basically these will be reverse bias, so that no current should flow into the in this way directly. So this should be negative and this should be positive. Okay. Similarly over here, this will be, actually this should be positive. Reverse bias, right? Like this it will be, yeah. Orientation was slightly different. It will be like this. Now they are oriented differently. Okay. So this MOSFET utilizes the reverse bias PN junction in the operation. Whereas BJT, it's unique in that it utilizes a forward bias PN junction. Forward bias junction, and therefore the injection of carriers across the junction. So two things happens over here. The first, the forward bias, we forward bias the base emitter junction, and the entire process results in a injection of charge carriers. Injection of carriers across both the junctions. Okay. So this will result in, there are following consequences point. This will result in higher, BJT will have a higher GM than MOSFET. These are important point. MOSFET is metal oxide semiconductor field effect transistor. Okay. More complex fabrication. So fabrication wise, fabricate means how we make the devices. This is a disadvantage. Fabrication is complex in case of a BJT. It's easier in MOSFET. Then it will have low input impedance. Low input impedance of a BJT. Okay. Why? As they are current control devices, right? BJTs are current control devices. That is why it offers low impedance. Current controlled device. The next point is high current capability. Higher current capability of a BJT in comparison to a MOSFET. Why? High current capacity in BJT, because GM is higher. Just now we said, right? GM has to be high. Okay. So higher the for GM, delta IV, delta ID by delta VGS. So if I have a higher value of GM, that means my current capability of the BJT increases. Please write this points. Point number 5, comparison to MOSFET. It is generally faster switching times. Okay, so it has faster switching capability over MOSFET. Okay, BJT have large size. larger physical size than MOSFET. MOSFET as having a larger space or area. I mean, the BJT will have a larger space area physically compared to a MOSFET. So these are 5, 6 points which makes BJT superior over MOSFETs. All right. Now let's go for the basic structure. Everyone ready? Hello, you all are listening?
Sir,
Yes? Doubt?
like if like I like is size the only trend for choosing MOSFETs in smaller devices than
Yeah,
BJT?
size is the main reason. Size is the main reason. Because MOSFETs can be scaled down up till we have verified up till 2 nanometer, where it is not possible in case of a BJT. Okay, it's larger size due to it's how it works. Now let me show it to you the basic structure of a BJT. How do you know a basic structure of a BJT? This way, right? If you think this is the structure, you're wrong. This is just the 1D view of it. Okay, so this is, let's say this is N plus, this is P, and this is N. Okay, this is my collector, this is my emitter, and this is my base terminal. Yes. Now in modern day, this is not a BJT structure actually, how it is fabricated. So BJT are fabricated for integrated circuit applications in this form, the way I'm showing it to you. It's a planar process. Okay, so we take a big semiconductor substrate, all material made up of semiconductor substrate. Okay, we call that region as, let's say, P device. Then we have, let's say, the string. Then we make a layer of N. Then again we make a layer of P. And finally we make a layer of N plus. Okay. So the first one is actually quite large. I see. So what is the first tapping over here? This is my base. Actually, I should have drawn it according to this, but it's just fine. So this will be my what? This is, oh sorry, this will be my emitter. Inside I have an emitter, then the base material, and then the collector. Okay, this is the basic structure fabricated, BJT fabricated for IC applications, which is the planar process. All right. Here the base region is non-uniformly doped. Okay. So this results in a built-in electric field across the base, which aids the transport of electrons from emitter to collector. So inside this base terminal also we have parasitics involved. You know what are parasitics? Which are inherently present in the device. So these parasitics will be responsible for the fall of gain in higher frequency range. Yes or no?
Yes,
Hello.
yes, sir.
Okay. Okay. Now, is this clear to you? This is how the BJT has been made, fabricated. It involves complex steps, more complex than a uh, MOSFET itself. Can I scroll down?
Yes,
Now we'll try to understand the basic operation of BJT. So let's write last topic for the day. Basic we have basic device structure and fabrication we have seen. Now we are seeing the transistor action. So next lecture we'll see minority carrier distribution and common emitter DC characteristics we have already covered. Okay, basic operation of BJT. All right. So for that, let me draw this diagram. It's easier to explain it using this diagram. Okay, that's why we are drawing it. No other reason involved. This is my collector. This is my emitter, and here I'm applying only VB, which is around 0.7 volt. We know that. This is N plus P N. Okay. Can we start with the explanation?
Yes, sir.
So listen carefully. The BJT basically operates as follows. So as the external voltage is applied across the emitter base junction, there is a forward bias to forward bias it. So there is an emitter base junction over here. Let me draw it with red color. Here it is. This is what? Base emitter junction or emitter base junction. So as an external voltage is applied across the base and the emitter terminals, the base emitter junction is forward bias. So the electrons are injected into the base by the emitter like this. So there are electrons over here. They are being injected into the base terminal. Agree? So the electrons are injected into the base by the emitter, and holes are injected into the emitter by the base. So holes are injected. Where are the holes over here? Holes are also injected into the emitter by the base. So there is a small quantity of holes which are injected back to the emitter terminal. But the numbers are much smaller because of the relative values of Na and D. So I've told you now the minority and majority carrier concept. So if ND is around 10 is to 16, what is the minority carrier concentration given by? Anyone can tell me? Minority carrier, this is ND.
Yeah.
So it will be majority carry upon Ni square, right? This is 10 raised to very high value. So minority carrier concentration is very small over here. So that's why their numbers are small. So the holes which are injected into the emitter by the base, their numbers are very small. If WB is less than Ln, now what is WB and Ln? See, WB is this. There is a depletion region here also formed, right? And what is my width of my base region? Here, this is the base width, WB. So WB is the base width. Okay. So Ln is, I will talk about Ln. I think Ln I have already discussed now in the PN junction. What is Ln? Diffusion length, right? The length over which the carriers will travel without recombining. Are you understanding? The length over which the carriers will travel without recombining is Ln. So if WB is very small compared to Ln, most of the injected electrons get to the collector without recombining. What is that meaning? What is the meaning of that? Let's say Ln I'll talk about. Ln is profile is like this. So the Ln will be over here, right? Like this. This will be Ln up till here. So what does this mean? That the carriers are getting over by this period, by this length. So if WB is very small compared to Ln, then what will happen? The carrier concentration is dying fast. Oh, sorry. Decaying fast. Why? Because they can recombine with the holes na, in the base terminal. So if WB is less than Ln, then most of these injected electrons get into the collector without recombining. Did you understand? So here most of electrons reaches the collector terminal. Okay, now recombination कैसे होगा? This holes, here the recombination happens. So for recombination and emitter injection, here it happens. Recombination. So maybe 5% of them will recombine with the holes over here. 95% of these injected electrons will go to the collector terminal, are collected by the collector terminal. Got it? So again I repeat, if WB is less than Ln, I'll talk about this point later again. Most of the, let us write this, if WB is less than Ln, most of injected electrons get to the collector without recombining. Okay, a few do recombine, few of them do recombine. The hole necessary for this are supplied as the base current. Whichever holes are recombining, they'll constitute the base current. Okay, are you understanding? Yes or no? So the holes which do recombine will contribute to IB, the base current. Now, the electrons reaching the collector are accelerated towards the collector base depletion region. Why they are accelerated? Because there the depletion region width is very large. So the electric field in that region is very large because it is reverse bias, right? Because we reverse bias this junction, right? Further. And reverse bias voltage is very large. So this field is very large. So whatever electrons are coming into the base, they have been taken away to the, pushed away to the collector region. Okay. Now, since most of the injected electrons reach the collector, only a few holes are injected into the emitter terminal. Okay. That is why we have IC very much greater compared to IB. Are you getting it? Why we have this term? This is in milliampere and this is in microampere. This is the reason why. Most of the electrons go into the base and then into the collector. Very few recombine in the base, which constitutes the base current. Okay, so the injected electrons reach the collector and only a few holes are injected into the emitter. Okay, that is why the device has a substantial current gain, which is beta, IC upon IB. Okay, is this is smaller, then the gain will become even larger. Are you understanding? Internally, the controlling parameter is VB. So here in this device, your controlling parameter is VBE, will determines the injection level. Okay. So usually the device is current control device, but who is controlling the current? VB. So basically VB is controlling IB and IB is controlling IC. That's why it's called as a current control device. Got it? Hello. Are you understanding?
Yes, sir.
All right. So what we will do is we'll stop over here and next time we'll talk about the transistor action, minority carrier distribution, and then possibly on the same day, that is tomorrow, Abor small model and hybrid pair model. That will complete the major chunk of from module number 3.2, 3.1. All right. So that's all for today. Tomorrow, same time, we will rejoin. Okay.
Yes, sir.
So yeah, thank you all for joining.
Thank you, sir.
Thank you, sir.